right, so here is a quick review for exam 3, about 10 questions on momentum, linear momentum, that is, rotational motion, angular momentum, static equilibrium, and fluids. All right, so first of all, we're going to look at conservation of momentum. We know that the total momentum before collision is equal to the total momentum after collision. And also that there are two types of collisions. One is an elastic collision where kinetic energy is conserved, and the second is inelastic collision where kinetic energy is not conserved. That means kinetic energy is lost, or the final kinetic energy is less than the initial kinetic energy. So that is what we're going to look at. So here is the conservation of momentum. m1v1 plus m2v2 is m1v1 prime plus m2v2 prime. v1 prime and v2 prime are the velocities after collision. And then you see the difference between elastic and inelastic. So here's the first question. So I'm trying to make this question diagrammatically so there won't be words and sentences. So there is a 3 kilogram object moving at 20 meters per second to the right or to the east. Well, there is a 2 kilogram object moving at 10 meters per second to the left or to the west. So there A and B, and after collision, the velocity of object A is changed to 5 meters per second. So object A after collision has a velocity of 5 meters per second, and you're asked to find the velocity of object B after collision. So what's important here is to take note of the directions. Going to the right is positive, coming left is negative. So that's what you have to be careful about. So when you apply the conservation of momentum, you see m1 v1, 20 is positive, plus, I changed that, that's why you have this as positive 5 now, and then you have 2vb. So that gives us 12.5, and then went ahead, found the initial kinetic energy, which is half times m times v squared. And when you take the kinetic energy, you need not consider the sign of the velocity because a negative squared is a positive. So went ahead there and found the initial kinetic energy as 700 joules. That's the total initial kinetic energy. And then the final kinetic energy is 193.75 joules. See where I've used the square of the velocity of the second one after collision. So there is a loss of kinetic energy of 506.25 joules. So this is an inelastic collision. So whenever you're asked to find the loss of kinetic energy, that's what you do. First you find the final velocity, which is unknown, and then find the total kinetic energy before and total kinetic energy after. Take the difference. That is the first one. Now, in the second one, we are going to look at the acceleration of an object that is rolling down an inclined plane. So, if an object is sliding down an inclined plane without friction, we know the acceleration is g sine theta. Because we've done that before. But here, there are two differences. Number one, it's rolling down. Number two, there must be friction for it to roll down, because otherwise it'll just slide. So two differences. So we're going to look at that. We will get a general formula for acceleration of any rolling object down an inclined plane. So let's derive that formula. And here is the incline. So that is a disk or a sphere, whatever you want to take it as, has a radius r, and it's rolling down. So here you see the forces that are acting. Of course, this is friction acting up the plane. You have the weight, and we know that the weight is resolved into its components, mg sine theta and mg cosine theta. And then you have the normal force. All right, so those are the forces. That's the weight. The angle is theta. This is mg sine theta. And then you have mg cosine theta, friction, and the normal force. So when you consider the torque of friction, the torque created by friction at the axis, which is here, you know that the distance is the radius. So, torque is the product of the force and the perpendicular distance. So it would be F multiplied by R, the radius. But we also know that torque is I alpha. I alpha. So there are two formulas for torque. And alpha is A divided by R. Okay? A divided by R. So from here we get A is alpha R. So we're going to substitute that there. So we know alpha is A divided by R. I've just written that down. And so let's substitute the value of alpha into that equation. When you substitute the value of alpha, you get F times R is I times A by R, because alpha is A by R. That's equation 1. And next we know that the net force is mg sine theta minus F. Mg sine theta down and F up. So now we're looking at the forces, not the torque. And that, according to Newton's second law, should be equal to mass times acceleration. Okay? Net force is equal to mass times acceleration. So we got that. And then we will substitute for friction. We got friction as IA by R squared, because when you bring this R down, it becomes R squared. So that's what I've done. And then some algebra there. Mg sine theta is equal to MA plus IA by R squared. When I take it to the other side, now there is A common, so that is taken out. M plus I by R squared is what I get. All right, and then on the left-hand side, I have mg sine theta. So when I rearrange, I'm going to get A is equal to mg sine theta whole divided by M plus I by R squared. So that is a very important formula to find the acceleration of any object that is rolling down an inclined plane. So here you see that I is the rotational inertia. So if we consider that it's a disk rolling down the plane, then we know the formula for rotational inertia of a disk is mr squared by 2. All right, a disk or a solid cylinder would be the same, because a solid cylinder is just a thick disk. So I is mr squared by 2. So if we now substitute the value of I as mr squared by 2, you would actually get the acceleration for a disk. So it's mg sine theta by m plus, where you have I, I'm going to put mr squared by 2, and then there's r squared down. Simplify that, the r squareds cancel out. And then in the denominator, you have m on both, so the mass will ultimately cancel out. And you get m taken out, 1 plus 1 by 2, which is 3 by 2, right? Okay, 1 plus 1 by 2 there. And the masses can be cancelled out. And then when you can flip the 3 by 2 to become 2 by 3 g sine theta. So that is actually the acceleration of a disk. But what if it's a sphere? What if it's a solid sphere coming down? Then we know the rotational inertia of a solid sphere is 2 by 5 mr squared. So we'll do the same thing, but in place of I, we're going to put 2 by 5 mr squared. So that's what we're going to do. So here is the general formula again. A is mg sine theta divided by m plus I by r squared. So that is the general formula. We start with that. And then for a solid sphere, I is 2 by 5 mr squared. So I is 2 by 5 mr squared. So once you substitute that for I, we can find the acceleration. So let's do that. So mg sine theta by m plus, right there I'm going to put 2 by 5 mr squared by r squared. Again, simplify, cancel the r squareds, and the mass will get cancelled, and we will get the final relation. So that's 1 plus 2 by 5 becomes 7 by 5. Mass gone. And you get, actually you get 5 by 7 g sine theta. All right. And if you consider that it's the angle is 10 degrees, I'm assuming that it's rolling down an incline 10 degrees, then you would get the acceleration as 1.21 meter per second squared. You see that as the angle increases, of course, the acceleration increases. So that's how we do that question. So in the next topic, we're going to talk about Young's modulus. We will talk about Young's modulus. You know, there are 3 moduli for inelasticity. Actually, Young's modulus, bulk modulus, and shear modulus. Young's modulus is when you have a cable that is rigidly fixed at one end, and at the other end you have a load. So you are kind of applying that force on the length, so the length has a small increase. So the length of a cable increases when you apply the force on the cross-section. So, and Young's modulus is linear stress by linear strain, okay? Linear stress by linear strain. And linear stress is F by A, and linear strain is change in length by original length. So when you put all that together, you get Young's modulus is equal to F by A, which is the stress, times the original length divided by the change in length. So that's a formula. And if the cross-section is circular, then the area is pi r squared. And if you're given a load, then F is mg. So when you put all that together, we should be able to work out this question. So the question says, a 0.6 millimeter diameter wire stretches 0.5%. See, the stretch is 0.5%. Means what? 0.5 divided by 100. So the change in length is 0.5 and the original length is 100. When it's stretched with a tension of 20 newtons, so force is directly given, and we have to find the Young's modulus. Let's do it. Young's modulus is given by this formula. A is pi r squared. It is the diameter that's given, so take half of that to get the radius, and then change it into meters, times 10 to the negative 3. So it's 1.4 times 10 to the 10. And did you notice that I have used 100 by 0.5? Because it's given us 0.5%. Okay, so that brings us to torque. How do you calculate torque? Torque is the cross product of R and F. Or it could be written as RF sine theta. The cross product of R and F, or RF sine theta, where theta is the angle between the distance R and the force. So you get maximum torque if the angle is 90 degrees, because sine 90 becomes 1. So let's work out a problem on that one. So here is the problem. You have a 95 Newton force exerted at the end of a 0.5 meter long torque wrench, which gives rise to a torque of 15 Newton meter. What is the angle? And assume that it's less than 90 degrees between the wrench handle and the direction of the applied force. So you're given the force, 95 Newton, you're given the length, 0.5 meter, and the torque, we have to find the angle. So look at the diagram. So here is the force, 95 Newton, and this is the distance at which you're applying, and that is the angle. So you're applying the force in that direction. Okay, and so here is where the axis is. And the distance is always from the axis to where you're applying the force. And then torque is Rf sine theta. And therefore, if you rearrange, sine theta is torque by R times F. Torque is given as 15 Newton meter. R is 0.50. Force is 95 newtons. I've written the units to see that the units cancel out, so you get sine theta, which is just a number, 0.316, no units. When you take the inverse of that, you should get the angle. So sine inverse of 0.316 gives 18.4 degrees, which is rounded off to 18 degrees looking at the significant figures. So that's how we do that question. Next, we're going to look at rotational motion. You know, there are kinematic equations in rotational motion, just like in linear motion. So if we have those formulas and we know those terms, it should be quite easy. You have initial angular velocity, your final angular velocity, angular acceleration, time, and angle. So here are the kinematic equations that are important. One is for angular acceleration, which is the rate of change of angular velocity. Then you have the formula for angle, which is omega it plus 1/2 alpha t squared. And then omega f squared is equal to omega I squared plus 2 alpha theta. So those are the equations. Let's see how to use that in working out this problem. The angular velocity of a rotating rigid body increases from 500 to 1500 revolutions per minute in 120 seconds. What is the angular acceleration? So we're looking for alpha. And we need omega. But what is given is not omega. What is given is it's at 500 revolutions per minute. First of all, per minute is not correct. We got to change it into how many per second. And then we have to change it into angular velocity, using the idea that omega is 2 pi times the frequency. So when we get revolutions per second, that's going to be the frequency, multiplied by 2 pi to get the angular velocity. Let's do it. So the initial frequency is 500 by 60. That's because you're trying to get it per second, which is 8.33 rotations per second. The final frequency is 1500, which is actually 3 times that. Could have done it that way. 25 RPS. So the initial angular velocity omega I is 2 pi times Fi. You get 2 pi times 8.33, which is going to be in radians per second. I just left it like that. And omega final is 2 pi times the final frequency. Again, 2 pi times 25 radians per second. Now that we have both of these, we can find alpha by omega f minus omega I by t. The time was 120 seconds. So now I've taken 2 pi out. That's why I left it like that. Take the difference divided by 120. And the calculations come out to be 0.87 radian per second squared. Next, we got to find through what angle does it turn. So theta. Theta is omega it plus 1/2 alpha t squared. Omega I is 8.33. The time is 120. So 2 pi times 120, because we need omega I, plus 1/2 alpha. We got alpha as 0.87, so that's why you have 0.87 there, t squared. When you do all that carefully, you get 12545.5 radians. So that's the total angle. So let me go one step ahead. Although I've not done it, let me ask you this. If you were asked to find out how many total rotations it made during this time, Would you be able to do it? Yes, because we know that 2 pi radians is one rotation. So once you get the total angle, you just divide it by 2 pi and it'll give you the total number of rotations it made before it came up to that speed. Should be able to do that. All right, let's move on to the next one. The next one talks about angular momentum. Angular momentum is the cross product of r and p, where p is linear momentum. And what is linear momentum? It's mass times velocity. So, r cross p, so which is r cross the linear momentum, and linear momentum is mass times velocity. So let's work out a problem. So here you'll have to use the cross product. So at a particular instant, a 1 kilogram particle's position is, so that's r, 2i minus 4j plus 6k. So you have the position vector. Its velocity is negative 1i plus 4j plus 1k meter per second. And you also have the force. The force is 10i plus 15j newtons. So there are 3 parts for this question. In the first part, what is the angular momentum of the particle? So for the angular momentum, you take the cross product of r and p, where p is mass times velocity. Okay, so here it is. Angular momentum is r cross p. And r is 2i minus 4j plus 6k cross, now p. You got to take the mass, which is 1 kilogram. Because it's 1, it doesn't change the number, but you still got to do it, times the velocity. Because p is mass times velocity. So that is going to be, okay, I've taken the mass out. Now you take the cross product using matrices, right? So you put it in the matrix format, ijk, and then you take the coefficients, and be careful about the order. So look at 2, 4, so that's actually negative 4. 2, negative 4, and 6. And then you have minus 1, plus 4, and 1. All right. So I into 4 minus 24. Have I forgotten the negative there? Let's see. Okay, I put the negative. And then here you're going to see negative 4, 2, negative 4, 6, negative 1, 4, 1. So follow along. To find the coefficient of I, you go negative 4 times 1 minus 6 times 4. So that's what I've done. Now to find that of j, remember to put a negative, and then you go 2 times 1 minus 6 times minus 1. So that's how I got 2 plus 6. And for k, you go 2 times 4 minus negative 4 times negative 1. So there it is. Be careful with the signs, and you would end up with this. So that is the angular momentum. In the B part, you're asked to find the torque. Now, torque is the cross product of R and F. So that's exactly the same thing, except that you have the coefficients of R, 2, negative 4, and 6, and then take the coefficients of the force. Force is given as 10I plus 15J. So you got 10 and 15. There is no K, so that is 0. And then do the same that I did. You know, to find the coefficient of I, go minus 4 times 0, that is 0, minus 6 times 15, that's why you have minus 90, and the same thing across, and you would get the torque. So that is an important question. So there are 2 things. To find angular momentum, you got to take the cross product of R and P. To find torque, you got to find the cross product of R and F. That brings us to the next question. Here is the question. while spinning down from 500 RPM to rest. A solid uniform flywheel does 5.1 kilojoules of work. All right, work is equal to change in kinetic energy. So if it does that much work, that is its kinetic energy. Because finally it stopped. So it had that much kinetic energy. It says if the radius of the disk is 1.2 meter, what is its mass? So what do we have? We have the RPM. The initial is 500 RPM, from which we can get the RPS, which is the frequency. So that'll give us omega, because omega is 2 pi times the frequency, isn't it? And what is the final angular velocity? 0? Yeah. So we have the initial angular velocity, and we have the final angular velocity. We should be able to find alpha. Okay, so we have the kinetic energy. The radius is given. How do we find its mass? So work, in linear motion, work is the dot product of force and displacement. But in rotation, work is the dot product of torque and angle. Force is replaced by torque, and displacement is replaced by angle. Omega 1 is 2 pi times frequency, which is 500 by 60 RPS. So that gives us omega 1 in radians per second. Omega 2 is, of course, 0 because it stopped. And the kinetic energy is given. Kinetic energy, see, first I wrote work, and then I said, because we know work is the change in kinetic energy, we can use kinetic energy, and which is 1/2 I omega squared. So I is mr squared by 2. Why? Because it is a flywheel, which is a disk. And the rotational inertia of a disk about an axis through its center of gravity is mr squared by 2. So that's why I is mr squared by 2 omega squared. And that is, we don't know the mass, we know the radius is 1.2 squared by, put that 2 there, and we got omega. And we are given the kinetic energy as what? 51, no, actually it's 5.1 kilojoules. Kilo is 1,000, so that makes it 5,100. And then do the math. I don't want to read the math. When you do the math carefully, you will get the mass as 5.167 kilogram. And then again, although I wrote work first, and then I said work is change in kinetic energy, that's why I went to the formula for kinetic energy. I hope it makes sense. That takes us to the next one. Okay, in the next one, the mass of a floating object is equal to the mass of liquid displaced by it. What comes to your mind? This is Archimedes Principle. So we are in fluids. Whenever an object floats, the mass of the floating object is equal to the mass of liquid displaced by it. So here we got to be careful because you have a solid and a liquid. So would we take the entire volume of the solid? No, we only take the volume of the solid which is under the liquid. But if it's a helium balloon, then the whole balloon is in air because the fluid is air there. So then we would take the total volume of the object. So read the question and look at it and see which volume you should take. If the whole thing is floating, submerged, like the helium balloon, then you take the whole volume. But if the problem says only half of the solid is under the liquid, then you take half the volume of the solid, because that's the volume of liquid displaced. All right, so here is the example that I want you to do. A spherical balloon has a radius of 7.35 meter and is filled with helium. All right, this is the same exact question we did in class. How large a cargo can it lift, assuming that the skin and structure of the balloon have a mass of 930 kilogram? Neglect the buoyant force on the cargo volume itself. So mass of the object in this case, there will be 3 parts. First, we have the mass of the skin and structure, which is 930. Then you have the mass of the helium inside the balloon, which we have to find. And then we have the mass of the cargo. So there are three parts. So on the left side, you have the total mass of all these three. And on the right side, it should be equal to mass of fluid displaced. In this case, the fluid is air. So it will be equal to the mass of air displaced. Okay. So you have all the three. And that's what I'm writing here. So on the left side, well, my left and right changed here. So you have the mass of air displaced on the left side. Mass of air. How do you find mass? Volume times density. So volume of the balloon times the density of air times g. So that gives you the weight of air displaced. Now you will see that you can either say mass or weight because g will cancel out from both sides. So here I'm writing the weight of air displaced is equal to the three parts that I told you, the mass of all those three added up times g. G cancels out. And then the volume of a sphere is 4 by 3 pi r cube. 4 by 3 pi r cube. All right, so when you do 4/3 pi r cube, put the radius as 7.35, and that comes out to be 1663.2 meter cube. And so we got the volume, and that is the volume of the air. The density of air will be given. It's 1.29. That is the mass of, we're trying to find the mass of helium because the volume of helium is the same. Times the density of helium is 0.179, which will again be given, plus the mass of the balloon, which is the mass of skin and structure is 930, and then the mass of the cargo, which we are trying to find. So do the math. Left-hand side, 2145.55. On the right-hand side, multiply those two, I get 297.7, and then add those two, bring this to the other side, so you will get this number minus this. Okay. And that was going to give us the answer. So look at how simple it is if you understand. The total mass of the floating object is equal to mass of fluid displaced, or the total weight is equal to the total weight of fluid displaced. Right? That's the last one, which is dealing with equation of continuity. Equation of continuity, where if you have a wide pipe and a narrow pipe, the volume of liquid flowing through both will be the same. And it's given by A1 V1 is equal to A2 V2. And then Bernoulli's principle, for a horizontal pipe, we don't take the potential energy term, remember? So it's only the pressure and the kinetic energy, and it comes out to be P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. What are they? P1 and P2 are the pressures at the wide and the narrow. V1 and V2 are the velocities at the wide and the narrow. So if you can situate what they are in the problem, it should be quite easy. All right, so here it's a combination of these two that we're going to use. The white part has a diameter 6 centimeters. This again is the exact same problem we did in class, okay? You have the diameters as 6 centimeter and 4 centimeter. And then you have the pressures given as 32 kilopascals and 24 kilopascals. So you have P1 and P2, you have the radius, and we have to find the volume rate of flow. What do you mean by volume rate of flow? It's either A1 times V1 or A2 times V2. Do we know A1? Yeah, we can find it because it's pi r squared. We can either find A1 or A2, but we do not know V1 and V2. So that's where we have to combine these two equations, okay? So that's the wide part, here's the narrow part. 6 centimeter and 4 centimeter are the diameters. And we know that the volume flowing by the time is A1 V1 or A2 V2. All right, pi times 3 squared. I am keeping it in centimeters because if it's centimeters on both sides, it's okay. Be careful, all right?
Range, you get v1 squared by 2 minus v2 squared by 2. And do the math. I'm taking the 2 from here to the other side. So it becomes 2 times p2 minus p1 by rho. And I just did v2 is 9v1 by 4 because I want to substitute for v2. So look at that. Since we have v2 squared here, I had to square that. So 9 squared is 81, 4 squared is 16. That's how I got that. And on the right side, it's 2p2 minus p1 by rho. So there's only v1 here now. See, I'm trying to solve these two equations, and I have to go to the next page. I take v1 squared out, so that's 1 minus. That is the 81 by 16 that you see. 81 by 16 is p2 minus p1 by rho. There is the 2 there. And then I will be able to separate v1. That's my aim. Because once we get the value of the velocity, we can just multiply it with a1, because a1, v1 gives us the answer. So all that math goes into that. And 1 minus 5, that is what gives me negative 4 and all that. And p2 minus p1 is also negative. So the two negatives will make a positive. So 24 kilopascals is 24 times 10 to the 3, minus 32 kilo is 32 times 10 to the 3. And so density of water is 10 to the power 3, which is 1,000, right? So you see that the top is also negative. So finally you end up with the square root of 3.93, which will give you the velocity as 1.98 meter per second. Yes, there's a lot of calculation that you have to be careful about. And so finally, to find the volume, you take the area of cross-section of the wider part and multiply it with the velocity. So A1, V1. So that is pi times 0.03 squared times 1.98, and that will give you the answer as 0.0056 meter cube per second. Thank you. I hope you understand all these problems and how they worked out. Like, I had to go a little fast, but you can pause and look at those problems and see how I got the answers. And this will be a good review for exam 3. Again, if you understand each step, do not try to memorize, because the problems on the exam are not exactly the same. It's just not the values. It's also the sentences that change, so you got to really understand. So wish you all the best, and we'll see you on the next video, which should be the final exam review. Thank you.